I'm going to finish up the lecture from last class period, which unsurprisingly is actually going to be a pretty long lecture. And then we're going to do the experiment. Hopefully the lecture helps the experiment to go faster for you as you understand things better. So we ended up with just 2 slides from this chapter, so that's why I'm going to the beginning. Just talking about the relationship between a pure substance. Now, pure substance is not elemental necessarily. Elemental is pure, but you can also have a pure compound. So you can have pure water. It's a pure substance. Something that the book emphasizes is there has to be a limit to our purity. 100% pure is practically not attainable. You're always going to have one atom out of, the entire batch of water that's not water. And so, or one molecule that's not water. So, 99.999% pure or something like that. It's never going to be a perfect 100. Just want to make sure people aren't sitting here saying, but that's not possible. You can't be perfect. So a pure substance will be something that is essentially all one substance. Whereas a mixture is 2 or more molecules. And they can be separated by some kind of physical means. That physical means could be a filter. I was talking to Maggie earlier about what we're doing in class today. It's like separating coins. And you can separate coins by size. And you make a filter, says if it's bigger than this or smaller than this, and separates quarters and nickels from pennies and dimes. And then you take the quarters and nickels and separate them by size. That's a physical separation. One of the common ones we use in chemistry is a centrifuge. A centrifuge spins things really fast. So it makes it so you have a really large acceleration. So the effect of lower mass floats or lower density floats on higher density becomes a much bigger effect to help you separate low density from high density. That's a physical separation. And that's not what I meant to do. So we saw this picture here of sugar. Sugar molecules, when you just have a cube of sugar, they're all packed together nice and tight. When you put them in your coffee or tea or whatever your bad beverage, please no food or drink from now on because we're going to have chemicals. And there were chemicals already yesterday. So that's the reason we have the rule in this building for no food or drink at the black tables to keep things safe for the students. I have to remember because I've been really lax in enforcing the rule. So when you put the sugar in your beverage, the water molecules then start separating the sugar molecules. So you have a sugar molecule here that's being surrounded by water molecules. And so now the sugar is going to be dissolved in the water. Now, a lot of vocabulary here. I went through and tried to underline words to make things streamlined as I talked. A mixture can be heterogeneous or homogeneous. Hetero means different. Homo means the same. So homogeneous means that you have the same mixture of molecules everywhere you look. So you have, water and sugar spread out equally everywhere. If it's spread out equally everywhere, then it's going to be homogeneous. Heterogeneous is when they're not the same everywhere. You can see, okay, this part's water and this part's sugar, and you can see that they're separated. So of course, this is in your textbook, a schematic just to identify differences in pure substances. You have elemental or compounds. You have mixtures that have homogeneous mixtures like air. Air is a mixture primarily nitrogen and oxygen. And you can't say, here's the oxygen, here's the nitrogen. It's all mixed together no matter where you look. So it's homogeneous. Suspensions are one I haven't mentioned. Milk is a colloidal suspension. You have little globules of milk fat, think of them like bubbles, right? Little balls of milk fat that are suspended in water. And so you can take that milk and you can separate the milk fat from the water through various methods. So that's a suspension, but it's so nicely mixed that you can't tell, oh, here's the water part and here's the milk fat part. But if you put it in the churn, right, you can start separating them. And then we have heterogeneous mixtures like sand and water. It's very clear. Oh, hey, look, there was a grain of sand. I felt it in my teeth. Right? The sand and water are discernible as separate and not together. Oil and water. What happens when you mix oil and water? Okay, the oil will float to the top because it's less dense. And if you mix it really hard, you'll still have oil droplets all through the water. And you can see, hey, look, there's a droplet of oil. There's a bunch of water. We say they're immiscible. They don't mix. And sand and salt. I would have liked it better if it said sugar and salt. If you put sugar and salt together, what's it look like? You can't tell the difference by looking, but in fact, this grain salt and this grain sugar, they are heterogeneous. It's just it's hard to tell. So here's some pictures to make the differentiation clear. Granite. Yes, we'll get to pizza. I had pizza for lunch. You guys know if you go to Da Vinci's, you got to say you're a Union College student and they give you 10% off, right? And this month, their pizza specials are the vegetarian pizzas because it's the month of Lent. So
Valentino's has a student discount too.
Do they? I did not know that. So if you look at granite, in this granite, you can see like here's something black, probably something like pitch blende. And you have this stuff here that's kind of pink color, plagioclase, I believe. And you have different compounds that are clearly separated in the granite. You can see they're different places. That's what makes granite granite. If you have them evenly mixed, you call it basalt. Same chemicals, but it's how it's mixed. So the basalt is at least closer to homogeneous. If you take exactly the same chemicals and you freeze them really quickly, it forms a glass, what we call obsidian. So obsidian, basalt, and granite, they're all the same collections of molecules. The difference is how they're mixed. In the obsidian, they're mixed so homogeneously that you can't see any differentiation at all. In the basalt, you have really tiny crystals that form so you can tell under a microscope that it's actually heterogeneous. And then with the granite, you can tell just by looking it's heterogeneous. Which, of course, that's something we're going to be covering later in this semester. The snow in the snow globe is clearly heterogeneous, right? You can see the snow. Yep, that's not water. That's whatever they put in there for snow. And, of course, the pizza. Yep, that's not crust. That's olive. Olives, bad. While we're at it, there is none but pineapple. It should be a sin to eat pineapple. I don't know why Leviticus law doesn't say that. Question. No, you cannot. Goodness. How would that help you on a test? Things that are homogeneous, air. The air, of course, is what we're seeing in here, not the hot air balloons. That's just to make it pretty. Water. The water there is all equally mixed. And, of course, the white gold there. White gold is not pure gold. It's a gold alloy, but you can't tell, oh, here's the gold and here's, what is it, platinum is the other metal in white gold? Does anybody know? I think it is, but I could be wrong. Okay, I already talked about the suspension, so I don't need to stay there anymore. We're not using the clickers today. Don't worry about pulling it out. So somebody blurt out to me, is the air in your house homogeneous or heterogeneous? Homogeneous. What was your key for saying it's homogeneous? Okay, I just said air is homogeneous.
You breathe it, and there's not like a weird gulp that's different.
Yeah, okay, that's a good. There's not a weird gulp that's different. There's not like that one there was straight nitrogen, right? Right. It's so well mixed you can't tell the difference. Okay. When you make solutions, this is one of the tests we're doing. We're going to take our unknowns. So the unknowns are up here labeled, this is sample 7, and we're going to take the sample and take a test tube and put just a little bit, and I'm actually going to do this, why not? Just a little pea-sized amount, so that's not very much. So just a little pea-sized amount of my unknown substance. That's too much. That'll do, I think. So I put that little pea-sized amount in the bottom, and then I'm going to fill it with water. Now, one of the things we learned from our trial run yesterday, for students involved in that trial run, because we were learning, is that the book's instructions just take it like this and go like that, wholly insufficient. Since we're just going to have water or alcohol in our substance, it's perfectly safe to touch that with your finger. Now, for other things we're using, you don't want to touch it, but this here, it's fine. So I'm going to go like this and shake it up nice and good. Why am I shaking up? Because I want it to dissolve if it will. And then I'm going to look to see if it dissolved. What do you see here? Nothing, it dissolved. Huzzah, this one was soluble. So that's how you're going to test the solubility. See if it dissolves. Now, some things will dissolve a little bit. Most of them will dissolve a very small amount. But you'll see, if you see a bunch of it in there, you're like, okay, it doesn't seem to dissolve. If you change the temperature, most things can be dissolved better. So we're going to have water in here that is like around 60 degrees Celsius. And for testing that, you're going to do the test differently. This time, how much did I put in? I put a pea size. You're only doing this test for things that had it dissolved. If I just leave that pea size amount, it's completely dissolved, I put it in hot water, if it dissolves more, I wouldn't be able to tell the difference. So for the test where you're testing dissolving in hot water, you're going to want, it says put in a few pea sizes worth. So, 3 times as much as you put in when you did this. You want to put in enough that it doesn't completely dissolve, even though it completely dissolved here. And then you're going to put it in the hot water. So you put it cold water in, and then you put it in the hot water and hold it there for a little bit so this water gets hot, and then you check and see, did more dissolve or is it the same? That's what that test is. Everybody clear on that test? Because frankly, yesterday I wasn't. What other test should I be doing with this? Just randomly choosing a person. I'm going to go with Carmen because I know she has hers done. If something is soluble, what's your next test?
To see if it has color or positive or negative.
For what?
Oh,
Which test?
for test 3.
Which one is test 3?
To see if it has color.
pH greater than.
Okay, the phenolphthalein one.
Sorry.
Okay, so for the phenolphthalein one, this here says phenolphthalein with a really crazy spelling. You pop the lid off. This one here you want to be careful with. If you and when you're doing this, I should be a good teacher. With chemistry, we are different rules than in physics. And one of them is in chemistry, we don't want to, I shouldn't say this because it's recorded. In chemistry, we don't want to hurt ourselves. In physics, apparently, we don't care as much. So when we're doing stuff in chemistry, we're supposed to have our eye protection on. So we have glasses up here for you all to use, obviously not to take home with you, for the lab. So now that I have my glasses on, the phenolphthalein, the thing to remind you of this is you don't want to ingest this phenolphthalein. You don't want to get it on your tongue, on your eyes, on anything. Because it's a really great laxative. Yeah. And also apparently slightly carcinogenic. So I put a little phenolphthalein in here. Woo! Look at that. What do I have, Carmen?
My favorite color. Either
I think it's washing soda.
washing soda or baking soda.
Okay, so it's either washing soda or baking soda. Depends on how dark it is. So for this one, you will say, okay, it turned pink. Say, is it light or dark? and then you're done with it. Now, what do? The next step is don't dump it down the sink. You know what? This is another. If we were doing this at home, we'd throw it down the sink. But because we're at a school, we have to follow some pretty stringent safety things. And so I'm pouring it into this here.
What mystery powder was that you were doing?
I didn't tell you which number. Maybe I did, but I didn't mean to. I put it back here and scramble them up. That wouldn't be fair because then it would be taken away from your experience, isn't it?
I think he's
So-
number 7.
According to this, right? So like, if it was washing soda, it's medium pink, baking soda would be light pink. So I mean, all others, the test is negative, right?
Right.
Okay. So
So
like,
you
there'd be
know it's
no
one of
pink.
those
There'd
two.
be no pink
There would
at
be
all.
no pink at all. That's correct. Okay, so I poured it into my reservoir here to save it. Now, before I use it again, if there's anything in here that I can tell is still in there, I want to make sure that I pour it in there. But if it looks like it's clean, I just doing my last stages of washing. There, I've washed it a few times, so it should be clean. Also, be very sure that you wash this thing between uses, because we don't want to take the powder from one and transfer it into the next. So I'm also going to wash this to make sure it's clean. And then I'm ready to go on. And of course, I chose the absolute best scenario here because I only had to do 2 tests there. Because the differentiation between the two that turn pink is how dark it turns pink. I don't need to do a third test on it. I just need to wait and see if I get another one that turns pink, if it turns darker or not. All right. So that was a little bit about solutions and saturation. If it's saturated, you have as much in solution as can go in solution, and so no more dissolves. So when you're doing the hot water test, you're going to have something that did dissolve. You put a bunch of it in, so it's not all dissolved. You heat it up and see if more dissolves. For most things, when you heat it up, more dissolves, but not for everything. Where's the graph? Here's the graph that deals with this. If you look at sodium chloride, as you change the temperature of the water, sodium chloride does not dissolve anymore. It's just independent of the temperature. Whereas if you look at something like sodium nitrate, that top one, the amount that you can dissolve doubles if you go from 0 to 60. Now we're going from 20 to 60, so it wouldn't double, but it would take up a lot more. So that's why we're doing that test of hot water dissolving, is to determine if it dissolves more when you heat it or if it doesn't. Now going back to where I was, the solvent is the major component in a solution. So when I put a little pea-sized amount of my sample in about 5 milliliters of water, which one was the major component? The water or the sample? The water, because there was a lot more of it. So that means that it was the one that we would call the solvent, because there was a lot more of it. The one that was the minor component then is the solute. So my sample was the solute. And we measure concentration by just taking the amount of solute divided by the amount of total solution. So the total solution is solvent plus solute. And so concentration can be measured in units like grams per liter, or there's lots of different units you can use, but it's the ratio of those. One of the ratios for measuring the concentration uses moles. So last class period, that's yesterday, I talked about the term mole. A mole, you guys may or may not have known who Dr. Friedlein was, but he had little visual aids. He had a little mole hand puppet, I think. This is a mole. A mole is a number of molecules. This number, 6.02 times 10 to the 23rd, is the number of molecules in a mole of a substance. So that number 6.02, there's more digits after that, is just a constant. And a mole is that many molecules. What's special about that mole is that it allows us to calculate mass. If I have 1 mole of protons or neutrons, it has a mass of 1 gram. Now, of course, as protons and neutrons have slightly different masses, it's not an exact equality. But a mole, well, 1 atomic mass unit, the things we actually measure the mass of an atom with, is this exact equation. So an example here is if I take carbon, carbon has 12 protons plus neutrons in its nucleus. And so if I have 1 mole of carbon, that's 6.02 times 10 to the 23rd atoms of carbon, it will have a mass of 12 grams. And sucrose is a sugar. This is its chemical formula. It's 12 carbons, 22 hydrogens, and 11 oxygens. It's kind of a complicated molecule. It has a total of 342 protons plus neutrons in it. So if I have 1 mole of sucrose, how much mass does it have? It's what?
1.
Not 1.
Formula mass of the substance expressed in grams. Oh.
This has 342 protons plus neutrons in it. So if I have a mole of these molecules, I have 6.02 times 10 to the 23rd molecules, each with a mass with a total of 342 protons plus neutrons. That's always going to give me a mass of that number in grams. Right? That's what the mole is about. The mole is the number that says if I have this many of the molecules, then its molecular mass is equal to the mass of 1 mole in grams. So as an example here, 1 mole of sucrose is 342 grams. Okay, that's just what I just said. This would be best if we had raised hands. If I have water that has a formula mass of 18, what does that mean if I say it has a formula mass of 18? 18 protons plus neutrons. Excellent. How many moles of water are there in 9 grams of water?
Doesn't make sense. It's A.
It's A. And how did you know it's A if it doesn't make sense?
I don't really know, to be honest. Well, because 9 is half of 18. Isn't a mole like?
So 1 mole of H2O
Is 18.
would be 18 grams. So since this is half of that, right? Which you did in your head, you just said you weren't sure. But good work nonetheless. Okay, molarity. One of the tests we're doing is going to be with, where is it? 0.3 molar sodium hydroxide. 0.3 molar means that it has 0.3 moles of sodium hydroxide per 1 liter of solution. So Dr. Osborne mixed this up for us so we could use it for lab, and he had to measure the mass of sodium hydroxide and measure the volume of water he put it into to get that 0.3 molar solution. So what does molar mean? It's moles per liter. And I am sure that Alex back there can tell you that there's not just molarity, there's also molality, and there is normality, right? I haven't learned that. And so they do try to confuse you with their terminology because molarity and molality, come on, too similar. For your case, we're just going to worry about molarity. You know, this one here, what does ppm stand for?
People per market.
Hey, 33% right there. The middle P is per. It's parts per million. This part here is exactly right. 1 part solute per 1 million part solution is 1 part per million. This part here is a little sketchy to me. 1 milligram of solute per 1 liter solution is making an assumption about the density. And that's not necessarily going to be true depending on what your materials are. So the one in dashed lines is not really perfect, but the one in the solid box is perfect. A part per million is just 1 molecule per million molecules is the one you're looking for. And so you'll see lots of things where they measure how much. Like if you look at the report of the water that we drink in Lincoln, Nebraska, or your hometown, every year they give us a report and it says how many ppms of calcium. Or it might say how many ppbs. What do you suppose a ppb would be? Part per billion, right? So that's another way of measuring the concentration. Already talked about this one. Precipitate. I had a student yesterday who was not sure on the word precipitate. I think everybody knows precipitation. If we have precipitation, what's happening? It's raining. So, yes, and the old man is snoring, which turns out is me. So precipitation is falling out. And when we talk about precipitation in chemistry, we're talking about a solid falling out of the liquid. So you saw I had a dissolved solution here. If I put the right chemical in, I may be able to form a precipitate and have a solid fall out. So it'll start snowing inside, if you will, and form a solid at the bottom. So that's what it means by precipitate. One of your tests is to put in a chemical and see if it precipitates. See if it has a solid that forms from that. And so this example here is just cooling sodium nitrate that's dissolved in water. At what temperature is it? Yeah, it's 100 degrees Celsius. The sodium nitrate is over 2 times more soluble than it is at actually it's not over 2 times. It's around 2 times more soluble than it is at 20 degrees. So you can have a saturated solution. Saturated means it's holding as much as it can. And then if I cool it from 100 degrees to 20 degrees, it can only hold about half as much. Notice the amount that it can hold goes from 165 to 87. That's about half. And what happens to the rest? It precipitates as a solid. We actually call that solid the precipitate. This is just a review question. Why can't you breathe underwater? Water's 88.8% oxygen. Why can't you breathe underwater? Okay, we don't have gills. That's right. But more importantly, I mean, air is only, what is air?
Because we have more than just oxygen in the air.
Yeah, we can't separate the oxygen from the hydrogen because it's not oxygen and hydrogen mixed together. It's oxygen, hydrogen bound together. We can't separate those chemical bonds. That take a chemical reaction to get us oxygen that we can breathe. Okay, soaps and detergents. I think this is cool. I actually spent probably an hour on these last few slides because I thought it was pretty cool. So, what does soap do for you? Clean stuff. How is soap traditionally made?
With animal parts.
Okay, it does have animal parts. You start with fat, And then in that fat, you put lye, and that's what forms soap. Isn't that good to know? Yeah, I don't want to eat soap. Don't want to eat that fat. That's how you make a soap. With the soap, you have a molecule that is polar on one side and non-polar on the other. So that the polar side will interact with dipoles. We put it in water. Water is a dipole, right? And so the polar side will be attracted to the water. The nonpolar site won't be. And so the nonpolar site will attack the grind. So you put your shirt in water. The water tries to wash stuff out. You've got this grind it can't lift. You put the soap in. The soap will come and you'll have the soap molecules, as shown in this picture, will have the nonpolar end stick to the grind. If I have the nonpolar end stick to the grind, what kind of attraction do you suppose is making it stick? Going through our sequence, we had, ion dipole, 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 induced dipole, and induced dipole, induced dipole. Which one of those do you suppose it would be?
Does this say grinds?
Yes, it says grind. Well, if the grind was a dipole, the water itself would attach to it, because you'd have dipole attraction between the water and the grind. So the grind that can't get removed has to be nonpolar. So I have nonpolar and nonpolar come together. What kind of bond, what kind of attraction can I have between two nonpolar things? Induced dipole, induced dipole. It's the very weakest one. But it's that induced dipole that's holding the nonpolar ends of the soap to the grind, and then the polar end is attracted to water. So essentially the soap connects water to the grind so that it then will have the grind flow out with the water. And so that's how the soap allows you to clean your clothes. It lifts the grime out and carries it away with the water. Now I have here the actual chemical formula for soap, which has the nonpolar tail, the part that has that induced dipole attraction to the grind, and then the polar head with the sodium there that forms the bond with the dipole. Detergents are just a little more sophisticated. It still has the nonpolar tail, but then it has a more polar head so that it's just a little more effective. So detergents are more complicated forms of soaps. Me, English. Oh, please tell me you all remember the answer to this. B, induced dipole. That's right. That's what is making the soap attract to the grind. And what makes the soap attract to water? A, dipole. Now, something that's cool, you guys like to blow bubbles, right?
Yes.
We did it in lab a few weeks ago. I had to spend 20 minutes trying to find bubbles. The soap that we put in those bubbles makes the water weaker. That is, you would have a stronger bubble without the soap. Is that surprising? Yeah. Most people think that the soap is what makes it so you can make bubbles, right? But the soap actually makes them weaker bubbles. So why do we use that soap? It's because the soap has the ionic side, or the polar side, and the nonpolar side. And when you blow the bubble, you're going to have a thin film of soap that forms on the inside and the outside, with the polar end in toward the water and the nonpolar end toward the air. What does that do? It keeps the water from evaporating, so your bubble doesn't evaporate and pop instantly. And so the soap makes weaker bubbles, but makes them so they don't pop instantly, so they will last. So when I was a kid, I always thought the soap made it so you could form bubbles. I was like, I'm going to put more soap in so I can make better bubbles. Does anybody else follow that logic?
Yeah.
What happens?
Can't believe it.
Yeah, it makes you make lamer bubbles. Why? Because it's weakening the soap, or weakening the force between the water molecules. So you're not forming as strong of bubbles. Okay, is this a pretty picture or what?
No. What is that?
Well, what it's not is teeth, because that's what this looks like to me. It looks like broken off teeth or something. It's not the mouth of some kind of, crazy sea animal. That is the inside of a pipe. And it has this layer that we call scale or lime scale. Over time, that layer gets thicker and thicker and thicker, occluding the flow of water through your pipes. What forms that layer? Well, lime scale means it's made out of lime, which is calcium carbonate. So it's calcium carbonate that was in the water that was precipitated, left as a solid as a rock. That's a good thing in terms of you and me living on Earth. Water will take carbon dioxide, attach it to calcium, and drop it as rock. And so carbon dioxide is cleaned out of the atmosphere and deposited as rock in the oceans. So we have less carbon dioxide in the atmosphere than we would otherwise. It's a bad thing in terms of pipes. So what do you do if you, by the way, we call it hard water when you have lots of calcium and magnesium. And that's what makes these films. That's what makes my beautiful beakers here. That's the calcium carbonate that formed from water having calcium carbonate in it. So what do you do at home if you have this hard water?
You CLR.
You what?
You CLR. Or get on a water softener.
Okay, I still didn't hear the first part, but I got the second part. Or get a water softener, which is what I was looking for. So you get a water softener. Come on, baby. What does a water softener do? The water softener has as its goal to remove the calcium from the water. And so you do something like try to take something sodium carbonate, NaCO3. You put that in the water, and you have two sodiums bound to the carbonate. There is a stronger attraction to a single calcium or a single magnesium. So that sodium will dissociate from the carbonate will grab up calcium or magnesium, and then you have the calcium carbonate and magnesium that won't deposit on the side of the pipe, but will just flow through. And so that's one way of removing calcium and magnesium ions. Here's the way a water softener works. You have these little, oh boy, I forgot the name of them, but these little particles in your water softener, and then you put salt with them. So you dissolve sodium, and sodium sticks to those little resin. That's what they call resin pellets. So sodium sticks to those resin pellets. And then as you have calcium and magnesium come by, the calcium and magnesium will displace two sodiums and replace the sodium. So now I have a magnesium here, a calcium coming in, and eventually all of my sodiums have been replaced by calciums and magnesiums. So what have I done? I put sodium in the water and taken out the calcium and magnesium, so that when my water goes through the pipes in the house, it doesn't have the calcium magnesium that will create those deposits on the pipes. Does this work? Of course it does, otherwise you wouldn't spend money. Here's my practical example. I've lived in my house for 14 years. The last 5 of them with my beautiful wife, Amy, who said to make today's class darn easy. Is that it?
No, darn good.
Darn good, okay. Yeah, so that's okay too. Okay. Well, about a year ago, she said, we need to get a water softener. The water in here is too hard, blah, 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 blah. So we got a water softener because, you know what, as I said before we got married, my wife was shopping for dresses and my sister called, we found this beautiful one. Can she buy it? And I said, What my baby wants, my baby gets. Dangerous words, it turns out. The dress was $1,000, and we had talked about prices and hadn't gone to that value. So she got the water softener, and within 6 months, I noticed something different in my shower. I have a shower head that has, a little thing that spins, so you have a pulsing thing. And it stopped spinning about 8 years ago. Why? Because of buildup of calcium carbonate. It started spinning again because my water was coming through with the calcium and magnesium removed. It actually started dissolving the slime scale that had built up on things. And so now I get my pulsing shower head back. Hey, yeah. And chemistry actually is cool sometimes, whereas physics is cool every time. Okay, that's just my bias talking. You know I'm joking, right? Don't want to go and say, yeah, he says chemistry is not as cool as physics. Well, that's why I joke. Yes, Jackie? Okay. Purifying water we drink. This is the next last thing. We're going to talk about purifying water we drink and then purifying water that comes out of our bodies. So purifying water we drink. First thing we want is water that's going to be safe for us to drink. We take it for granted that we can drink water out of the tap. But when we go to other countries, it turns out that in other countries, that's not something you take for granted. And after spending, we went on a trip with Honors a couple of years ago. After spending 3 weeks not being able to brush our teeth with water that comes out of the tap, it just felt wonderful to be able to brush your teeth. We take it for granted. Well, we have to go through some significant processes. You start with water. Unless you have a nice pure well, you usually have things in there like, Giardia and E. coli, things that you really don't want to take into your body. And so the first thing is slaked lime, which you can see the chemical formula for it there, calcium, CaOH2, that is Ca parentheses OH2. You have two OH groups attached to the calcium. That's the slaked lime, and aluminum sulfate, Al2, and then parentheses SO4, and parentheses 3. And when you put those together in the water, you have them separate and you form an aluminum hydroxide that's kind of gelatinous, right? It's kind of like Jello. And that starts to fall down to the bottom, but as it does, it collects stuff that's in the water. So you collect a lot of the stuff that's in the water and take it out of the water, giving you better water. Still not good enough to drink, but better. So then you want to do things like aerate it. That's actually, when you aerate it, you're just putting air bubbles through it. And the oxygen helps to remove and kill things that would give it bad taste and smells. And then you use something like chlorine gas or ozone to kill any remaining biology things. And you have drinkable water. Desalination plants are something that we wish we could do inexpensively. We have lots of salt water on Earth, but we can't drink salt water. Hence that really lame, riddle about water everywhere, not a drop to drink. Oh, you're out in the middle of the ocean, water everywhere, and you can't drink it because it's all salty. So how do you take away the salt? That's a chemistry problem. One way of taking away the salt is actually very simple: distillation. Distillation means that you evaporate the fluid, and different chemicals evaporate at different temperatures. So water boils at around 100 degrees Celsius. So if you heat that water up to 100 degrees Celsius, you're going to have a lot of water that boils out. Even if you only heat it up to 90, you'll have a lot of water that comes out as vapor. But the salt, it's not going to come out until you get up to around 800 degrees Celsius.
And then half the water's gone.
And your water should all be gone by the time you get to that point. Junior chemist Richard Webb, when I was doing the whole make salt thing when I was like 5 years old, well, not 5, 10, you put it on the stove and you have to wait 10 minutes. So you go out to play, an hour later I come back, and what do I have? Well, I did separate the water from the salt all right, but now we have salt cake on the bottom of the pan. That's what would happen if you were to get up that hot.
You had to get like salt water, obviously.
Yeah, it was just a little genius science experiment to show you can separate salt from water.
Oh.
So this here shows a simple design that's using solar power. You put salt water in there, it heats it up, water droplets go into the air, they condense on the glass in the top, it's sloped downward so they cruise down that slope, and you cast them in that little tray, and that's fresh water you see going into the jar at the end. Kind of a cool way to separate the water. Something you might see for people who are into outdoors is a variation where you use cellophane and you just take a pot and you put the cellophane in the top of the pot with a rock in the center so it holds it down in a V shape or cone shape. You put a cup in the pot in the center and salt water all around it. And pretty soon the cup will be filled with pure water because the salt water evaporates up, goes down the cellophane, drains down the middle into the cup. So that works, but it's not very rapid. So how do you do something better or faster? You ever heard of reverse osmosis? Reverse osmosis machines start with what's osmosis. We had to memorize when I was in high school biology, osmosis is the transport through a semi-permeable membrane from an area of greater concentration or less concentration to an area of greater concentration, something like that. Basically, with osmosis, you have a membrane that allows small things to go through, but not big things. And so with salt water, it allows the water through, but not the salt. And so when you put that in there, you can separate pure water from salt water. And the way it goes is you actually have water wants to go into the salt because you have more salt there, less water. And you actually form a different pressure, a higher pressure on the salt side than you have on the non-salt side. So the pure water side here is lower water level because it's lower pressure. Remember we learned water pressure difference was rho GH? Well, the reverse osmosis machines take that and they say, okay, let's just apply an external pressure on the saltwater side to force water through. Because the salt can't go through, we're just going to force the pure water from the salty side into the pure side. And so then you build up a bigger reservoir of pure water and you get saltier and saltier water on that side. And then, of course, you just clean it out and start over it. So that's a quicker way, more efficient way of separating it. Now the last thing, wastewater treatment. I'm going to go through this super fast. Wastewater treatment, that's where we take poop and we convert it into non-poop. So the first thing you do is remove the large insoluble items. Now, when I was in high school, we had our own sewer ponds there at Monterey Bay Academy. I will never forget Jimmy Nelson out there. You have to go out and clean a little thing in the center of the sewer pond. And so he and some freshmen were in this little rowboat to go out and clean it. He thought it'd be funny and all get out to rock the boat and scare them. There is a danger when you rock the boat. He capsized the boat. They had to swim to shore in human waste. Yes, I won't forget that one. It was funny. So the first thing you do is you have a screen to remove the debris. Things like, some people, you have toilet paper that goes down the toilet. You wanted to remove that stuff. So you have screens to remove that. But then you still have this fluid with all kinds of stuff that you would never, ever want to drink. And so you let it sit and have things settle to the bottom. Well, that stuff that settled to the bottom is pure, not pure water. And then you go through other steps. So here's the picture's worth many words. Here's the filter to take out things like toilet paper. And then here's a chamber where it just sits and you let stuff fall out. Here's a sludge pond. You have a skimmer going across the top, taking crud off the top. And you have really crummy stuff forming at the bottom that you don't want. They take it out of that, and then they put some chlorine in. What's the chlorine going to do? It's going to kill biological things like bacteria. But you're not done that. Next, you aerate it. You bubble air through it to try to kill the smell and things like that and bad taste. And then you go to another settling basin. And in here, we actually have bacteria that are working to help eat up the rest of the waste. When I was looking at this, I was like, why in the world would you ever take the stuff that settled out and put it back in? They're doing that to bring that bacteria that was helping to digest the crud in the water back so you have more of it instead of it disappearing. So that's just to replenish the bacteria. And then it comes out and you put more chlorine in it. And now we have secondary water. Secondary water, I believe you can put on a golf course. Right when it says reclaimed water, do not drink, that means it's been through this process. And I take it real seriously and I don't drink it. There is then the tertiary treatment that will make it so it actually is potable water. And if you're an astronaut, well, yeah, it's what you drink, right? What other choices do you have? Okay, that's my lecture part. Let's talk about the lab, and then you can do the lab and be out of here. So for the lab, we have 8 of these 9 chemicals. So you're going to have one that you don't know, or not one that you don't know, one that you don't find. We have some reagents. All of the reagents and stuff are in this cart right now. I will distribute stuff to you. Actually, I'll have Alex do it. Alex, why don't you start now? Give everybody 1 spatula, 1 test tube, 1 glass per person, and that's good to start with.
Every group gets a spatula or every person?
Yeah, every group gets a spatula and a test tube. And also give each group 1 of the unknowns. Groups of 2, of course. What we're going to do is we're going to test these. Remember, before you do anything, put the glasses on. Now, if you have small glasses like most of you do, put these on over them. They should fit. No, that's what I'm saying. If they're small ones like that, you want it, because we don't want stuff splashing in. It is safety. It's not necessarily comfort or happiness, it's safety. Well, this is pretty fashionable. I don't want to hear any slamming of the fashion statements here.
Can I get some water real quick?
Just wait till I finish. It'll be quick.
What?
Wait till I finish. It'll be quick.
Oh.
Okay.
Thank you.
You are going to then have to go through everybody I said before you come. Make your table. Look at your table. Look at your lab partner's table. Decide which one you're going to follow. There is not one perfect table. There are lots of variations that you can come up with. So look at your table, look at your partner's table, decide which one you're going to use. If it's your partner's table, make sure that you also write that table down as the one you're using. So when Alex is grading, he can see, yes, this is the table they did. Question? Okay, for the tests, I'm going to briefly describe each test so we're clear on how they work. So the first one, the solubility in water. Everybody saw me do the solubility in water. I don't know why, but it won't scroll now. I won't show you every test maybe. The solubility in water, just a little bit of the sample. Don't put in a big chunk, a pea size, right? If you put in a bunch, it's just going to have less that goes into solution. See, read one more. Yeah. Who else needs these? The printouts? Okay. So you put it in there. Remember I showed you about mixing it? Because the instructions that they give us for mixing were wholly insufficient to dissolve it. And if it is completely dissolved, like the sample I showed you, you'd say it's soluble. If it's mostly dissolved, I would say soluble or mostly soluble. If it's, not dissolved, if you have particulates that persist everywhere, then I'd say insoluble. So this is a judgment call, which I know judgment calls are always harder than when it's clear cut. Then you have the tincture of iodine test. Remember, you're not doing these 1, 2, 3, 4, 5, 6, 7. If you do all 7 tests on each one, you're going to get a really, really low score, right? In my formulation, it should take a total of 24 tests to completely test everything to see which one it is.
People who wear glasses need these.
Yeah, unless they have big glasses like the one yesterday. So make sure you follow through your table and do the tests necessary, but don't do extra tests. The tincture of iodine test, just put a single drop of iodine in your water. If you just dissolve it in water or try to dissolve it, and then you're going to do the iodine test, just leave it there, put 1 drop in. If it is the stuff that turns blue, you will see it turn blue. If it doesn't, it will stay brown. If you put like 5 drops in, it'll turn black if it's churning, right? So make sure you just put 1 drop. Now with iodine will stain your skin. So you want to try to not get it on your skin. It will also stain your clothing. Try extra hard not to get it on your clothing because your skin will slough off over time. Your clothing, not so much. The phenolphthalein test. This is the one here that is a laxative.
Everybody needs one of these.
Yes, everyone needs one of those. The thing he's giving you now is for you to report the results of each test you did.
Oh, does each person need one?
Each person, yes. For you to report the results of each test you did. So you can go through and identify which chemicals are which, how many tests you did, and so on. Okay, the phenolphthalein, it's a laxative, so be careful with it. Don't drink it. Don't get it on your fingers and then rub your eye, things like that. For the phenolphthalein, once again, you only need to put a drop in. You don't need to put, 5 drops. These bottles are dropper bottles. You flip the little lid off, turn it over into droppers so you can just put a drop in. The white vinegar test, come on. It does not want me to see the bottom part of this.
No.
I have no clue why it doesn't like this page. Look, I can mess with the other pages. I'm going to kill the program and try again because this is ridiculous. Come on, work this time. Woo! Okay, so for the white vinegar test, the white vinegar test can be done both in a liquid or a solid phase. Now, my experience is going out as a fake field geologist with a little bottle of acid. Vinegar is acetic acid. And putting that acid on rock and seeing if it bubbles. And it was very clear. If it bubbled, then it was calcium carbonate and it had carbonate. If it doesn't bubble, it doesn't have carbonate. From our experience yesterday, I think it works better to actually have your material dissolved in water and then just put the vinegar in the water and see if you have bubbles that form in the water because of the reaction between your sample and the vinegar. So that's how you're just going to do that one. Just put a few drops of vinegar in to your liquid and sample. The next one here is the sodium hydroxide test. The sodium hydroxide, this is a weak base. It's specific to the magnesium sulfate, which is found in Epsom salt. So this one is only going to tell you about one chemical, the Epsom salt. And if you have something that dissolves in water and forms an insoluble precipitate when you add this to it. So the sodium hydroxide test would be if it dissolves in water and you put the sodium hydroxide and then it comes out of solution and you form precipitate. Next to last, the hot water test. I already mentioned that. I will get the water going here in just a little bit. We'll have hot water up here. So you want to put, for the hot water test, you'll want to come up. You don't want to do this test very much because it uses a lot of the reagent. We don't want to run out. Or not reagent, it uses a lot of the samples. But you want to put a few peas, it says here. Place several pea-sized portions of the unknown solid, a lot more than you use for your initial dissolving test. And so then you're going to shake it up, and you should still have a bunch on the bottom because you put a lot in, so it's saturated. Then you're going to come and put it in the hot water, hold it, and it won't be so hot that it'll burn you to hold it here, until the water heats up. It shouldn't take more than, a minute or so for the water in your test tube to heat up. Take it out and look and compare. Is the amount of undissolved material less than it was before, or is it the same? If you have less, then it became more soluble, greater solubility, as it says here in the hot water. If it's the same, you had no effect. And if it's only a slight change, well, there's that. Then the final test, the rubbing alcohol. For the rubbing alcohol, you're going to do it just like you did the water test. You put a little pea size in, then you put this in. I found that my pouring was far less than satisfactory. So the one place where we're going to use these droppers is just to draw rubbing alcohol out of here and put in your test tube. Make sure that you close each of your containers when you're not using them. And like I said, it's very important that you clean your spatula before changing to a new sample so you don't contaminate the sample. Make sure you clean your test tube between samples so you don't have cross-contamination in your testing. When you're done, you should have identified what each one is. Notice this one should say table salt. It said table sugar here and here. That was a mistake. Should say table salt both places. The other mistake, as you may or may not have noticed, was one of these two results should have been insoluble in their little test. This is not what yours looks like, but it gives you what your layout looks like kind of for, your sequence. So then you'll come and answer the questions here. Which of the tests in the experiments measured physical properties and which measured chemical properties? Chemical properties are things that have to do with the molecules, their chemical structure. Physical properties are solid, liquid type things. Then sugar's a chemical, but it's also food. Is that contradictory? And explain. I talked about this in class yesterday, but make sure you have a good explanation about, sugar being a chemical and a food. And then how many individual tests did you have to do? Like I said, I have 24 on my sequence to identify all of the 8 that we have here. So you're going to see how many you had to do. Now make sure you do the tests you need to identify it. In the people that did yesterday, we had some cases where people did just one test, and that test left it. It could have been any of 3, and they just said, well, there it is. It must be this. Right? Make sure you do enough tests that you know which one it is. And if it could be 3, but you've already identified the other 2 it could be, make sure you make a note of that I didn't do the other test because I already knew it wasn't this or that. Of course, you could have made a mistake, so it's a little dangerous to make that assumption. That is it. Jocelyn. Okay, so you have your table of the order you're going to do experiments, right? And so you take powder 1 and you do the first test and you say, was it soluble or insoluble? So you'll write in there soluble or insoluble in the box for sample 1 and test 1. And then based on your table, you'll go to either, if it's insoluble, you go to either 3 or 5. And so then you say, okay, I next did test 3 and you put the result there. So you're going to put the result of each test in the appropriate grid. Yes.
So sample 2, so we put that on 2?
Yep.
Okay.
Any other questions? Okay, everybody have your glasses on.
No.
Put them on.
Are they?
Right in front of you.